been a long time since most classrooms shot real rifles in order to do this problem and study these variables. So there's a couple of common classroom demonstrators, and the two schools I've taught at, we've had both of them. And they're interesting in their own right because they introduce some variables. So I want to go through and show you the physics of the two that I've had to teach with over the years. This one is a very classic one made by Senko. We have it at Manchester High School. This one is a more common modern one that we had at my first teaching job at Southmore High School. And the way you measure how high the block goes is quite different for each of them. So we'll start with the Senko one. We'll talk about the extra physics we need to understand it. And then we'll look at the other one, and we'll talk about the physics we need to understand it. And we'll also use the other one to explain what happens if the projectile doesn't lodge in the block.
You break a complex motion into two pieces. You do conservation of momentum as the ball hits the target, and then conservation of energy as the ball and target together rise to a high point. But here's a kind of tricky question. Where is the object at the end? Is it here? Or is it here? Or is it here? Or is it here? In fact, it's in all of those places. We've actually been making an assumption all year that we can act as if objects are point particles, that they have a defined location, that a person flying through the air is at 0,63. Well, of course they're not. Each part of their body is in a slightly different location. This soda can, it has a whole range of y coordinates and a whole range of x coordinates. So why have we been able to act as if everything's a point? Well, up till now, most things have been like this soda can. They've been uniform, and they haven't had any sort of odd shapes. This is very different. It's got a lot of mass at this end where the ball and target are, tapering off to not that much as you go up to the pivot. So we have to start thinking about where is the mass of an object located. In reality, it's distributed throughout the object. But it's helpful to find an average location for that mass, where if you averaged up all the weight and position of everything in the object, you could say at this point is as if all the mass was there. And we call that point the center of mass.
So imagine I had a stick with almost no mass, and I put big globs of clay on it. Mass 1, mass 2, mass 3, mass 4. And I asked you to average out where you think the mass is. Not too hard to figure that out. It would be right in the middle. What would happen if there now was an imbalance in that clay? I think it's also pretty easy to figure it out. You would expect the average position of mass to be closer to the big glob than the little glob. Here's a really important trick, and it's the one we're going to use to find the center of mass of the ballistic pendulum arm. You can balance the object or hang it, and if it stays balanced, that means it's hanging or balancing from its center of mass. We'll talk about the physics of why that is later on. The way you can find it using an equation is you actually can take the average of where masses are. So I've got this somewhat intimidating looking equation here, but it's pretty easy to remember because average is just add up everything and divide by the total. And that's kind of what we're doing. So imagine I'm going back to the clay on a stick here. I pick a place that I call position 0, and I just multiply that position by the first mass. I add the second mass's term, the third mass's term, and I divide by the total mass. The way you could write that in shorthand would be this. I'm summing up all the mass times positions and dividing by the total mass. And if you were talking about a continuous object where the masses were infinitely small, which is how you describe a real stick that had mass or a baseball bat or something like that, this equation turns into this, where we have infinitely small slices of the object that have mass. There's equations for velocity and acceleration of the center of mass too. We'll use those a lot more later on in the class. But the key idea of the center of mass is you can say when you're putting forces on it and you're talking about where the object is, you could say that this is where the force of gravity is acting, and that's going to let us figure out how much potential energy our ballistic pendulum arm has. So, in order to understand our ballistic pendulum arm, we don't really have to think of two dimensions because it is long and thin. But while we're talking about center of mass, I wanted to point out that you have to find where it is in all dimensions of an object. So I have an object here which is essentially two-dimensional, this book, and you can see it's hanging at an angle. We can understand this angle just by understanding center of mass. As I said before, it will hang with the center of mass as low as possible. So that's why it's hanging down like this. If we graphically divide this book up into little pieces of mass, you can see I made it look like a grid of graph paper. And the average position of mass along the x dimension, which I called the top of the book, is the yellow. The average position of center of mass along the y dimension is the blue. So you can see the center of mass must be the green, and that's directly under the nail. So center of mass is pretty easy to find experimentally. Let's go back to our ballistic pendulum arm, and we'll just talk about it in one dimension, because that's all we need.
Although what's interesting is that this is pretty much a linear object, so we only really have to think of one dimension. We can call this the x dimension. For now, here's a trick for finding where the center of mass is. If I have an object and I hang it, the center of mass is always going to go as low as it can. This is on average where the mass is, and if you have mass higher than it is, if you give something potential energy and release it, that energy will transform into kinetic. And eventually, it will fall as low as it can go. So the object will always be as low as it can go, and that means the center of mass will be as low as it can go. So let's take our pendulum. We'll release it. And we'll find out where its center of mass is. If I hang it this way, it's pretty obvious that it's going to hang straight down. And that means the center of mass is along this center line. That's something we could have predicted. But what's interesting is we can locate it precisely if we hang it from a different point. Then there'll be another line that goes straight down, and where that line intersects with the center line, that's where the center of mass will be. Fortunately, the people who built this ballistic pendulum, Senko, they made this easy to do. They wanted you to get the center of mass, so they put a hook on the side of the pendulum. So you can see it's hanging at a particular angle. And it's doing that so that the center of mass is directly below the string. We can locate it precisely. I don't know how well you're going to be able to see this. By hanging another weight straight in front. And where the line of this weight intersects the center line of the pendulum, that's where the center of mass is. So in class we marked it with an X. The lab procedure Senko wrote for using this pendulum has you finding how far above the base that X is when it's down low, how far it is when it's up high, and that's how you're calculating potential energy. For a link to that procedure, see the description in this video.
So I'm not going to tell you how to calculate the speed of this ball because I want you to do that for yourself as the lab activity. This is the ballistic pendulum we have at Manchester High School where I am when I'm making this video. So I'm going to have students play with this themselves. In the prior video, you saw me do the calculation for the YouTube video with the .22 rifle. And later on in this video, you'll see me do the calculation for Southmore's ballistic pendulum. So you can use either of those as an example. But this is what I want you to do yourself.
We're going to revisit the ballistic pendulum I had at my first teaching job at Southmore High School, which worked a little differently. And there's a couple points that can be made about the behavior of the block and ball using that one.
This cannon fires a pinball into this acrylic block. Okay, it did. So, as you could see, the pointer went up to about 20 degrees, and we can use that with a formula which I'll teach in class and is on the next slide to calculate what the change in height for the block was. It's pretty straightforward to convert from the angle something swinging is at to how high it goes. And this is something worth remembering how to do because it gets asked a lot and it's just a common thing you should know. So what you need to do is you need to think of the object when it's hanging as low as it can go, which I've represented by this dashed line here. And then you need to think of it off to the side. So what we're interested in is the vertical distance between where it is when it's off to the side and as low as it can go. So we're going to do a subtraction there. The pendulum has a length L, and when it's as low as it can go, it's hanging from the top a distance L. When it's off to the side, it still has a length L, but some of that vertical has been turned into horizontal. So downward now we only have L cosine theta, and that means the change in height between here and here is L minus L cosine theta. So here's my calculation for one shot with the Southmore ballistic pendulum. You can see that I've got the mass of the ball, I've got the mass of the block, and I've got the length of the string as 0.21 meters. So I do my L minus L cosine theta and see that with the 20.5 degree angle I got, that it went up 0.0133 meters. I then do my quick conservation of energy calculation. I figure out how fast the block was moving before it started to rise, which I then scooch in as the final velocity for a momentum problem involving the ball hitting the block and combining with it. So I end up with a final velocity of the ball as 5.84 meters per second.
One last thing about ballistic pendulums, it's very important that the balls stick in the block, or else you have an issue where there's more impulse than you expect. I want to show you what I mean.
But now I'm going to deliberately alter it so that the bullet doesn't go in, and we should take a look at what happens to the height. So I'm just going to lay the camera down for a second, or maybe I can prop it up with this. So reset the pointer. Now I'm just going to drop the string a little bit so it definitely doesn't hit. And something really interesting is going to happen. So we'll pull it back to 2 clicks, which is where it was last time. All right, let's have a different shot now. So obviously this is not going to embed in the block, and I just want to see what happens to the angle. It goes a lot higher. And the reason for that, if you think about it, the bullet bounced. So it had to hit the block had to bring it to rest, and then it had to reverse its direction. And what that is a second dose of impulse. It had an impulse to stop the ball and a second impulse to knock it back. And the result was that the block had more of an impulse, and therefore it went higher. So if it ricochets backwards, typically we get too high an angle, and therefore too high a height change of the block, and it overestimates the speed.